Hello everyone, my name is Henry, and today we will be presenting about the applications of vector spaces in science and engineering. So here's our presentation roadmap. Our presentation contains three sections, which is the foundations, engineering, and science. And I'll be covering the foundation section. So the concepts that I introduce here will later be come back in the two sections later. So firstly, what is a vector space? A vector space V is a set of vectors that can be added and scaled, and the result will always remain within the vector space of V. And formally, there are 10 axioms that you need to verify before we consider it a vector space. But it is too time consuming, so we just narrow it down to three conditions. Firstly, the zero vector must exist, so that there is always a neutral element that you can add without changing anything. Next, we have the close under addition, which means that if you add two vectors within the vector space, the resulting vector will always also stay within the same set. And lastly, it is close under scalar multiplication. So if you multiply a vector within the vector space by a constant, the resulting answer will also be within the vector space. And if these three holds true, then it is a valid vector space. And these are the 10 axioms I was talking about, but I won't go through them individually. Here are some examples of a vector space. First, we have R2, which has a dimension of 2 because it has a basis of 2 vectors. And this spans the X and Y plane. Then now we have R3, which has a dimension of 3 because it contains 3 basis vectors. And this spans the X, Y, and Z plane. Then we have P2, which contains a polynomial of degree 2 or less and has a dimension of 3. And this is mainly used for curve fitting and the approximations. And what I'm trying to say is that vectors aren't just arrows within the space, but rather they apply to any set of objects that follow the three rules that I stated. Next, we have subspaces. A subspace is a subset of a vector space, which itself is a vector space, and it must also satisfy the three same rules that I stated. But the most important rule here is that the subspace must always contain the zero vector. So looking at the diagram here, this is a valid subspace because it goes through the origin of 0, 0. The line goes through the origin of 0, 0. And this red one is not a valid subspace because it does not go through 0, 0. And this is because that it does not fulfill the closure axiom requirements. And more examples is that any plane through the origin of R3 is also a valid subspace, and the set only containing the zero vector is the smallest valid subspace. So it is the smallest vector that you can get. Next, we have a basis span and the dimensions, which are three very closely related ideas. Firstly, we have the span, which is a collection of all vectors that you can build by scaling and adding vectors together. Then this answers the question of how much space can I reach with these vectors. And next we have the basis, which is a linearly independent set that spans the entire space. And this is the minimum building blocks to describe every point within a vector space. Next, looking at the diagram here, E1 and E2 is the basis for V because V is the linear combination of both E1 and E2. And next we have the dimensions, which is just the number of vectors in any space, or number of bases of a space. And in this case for V, there is a dimension of 2 because it contains 2 bases. And so why does this matter? This matters because engineers and mathematicians use mathematics to model the real world. So they are actually working within a vector space. So take electrical engineering, for example. The solution space for Kirchhoff's equation is itself a vector space. And structural engineering, which works with force vectors and load analysis, also rely on this vector space theory. And computer science, which has 3D transformations and color spaces, also uses this theory. Lastly, we have data science, which uses the least squares regression and principal component analysis. which rely on these vector space concepts entirely. So this isn't just theoretical, but rather they are actual tools that these fields use every day. With that, I will hand it over to Shava uh, for the engineering application section.
Good evening, ladies and gentlemen. Today I'll be talking about vector spaces in engineering. So, Andy has already given us the foundation of vectors. Now we're going to look at applications in electrical mesh analysis and structural stiffness method. These are two fields, but they all have one thing in common: this equation, AX equal B. So first we're going to talk about how vectors always obey positions, linear systems, which is the responsive sum of inputs is usually equal to the sum of its individual responses. This is exactly the linearity axiom of a vector space. So unknowns of the vector, whether it's mesh currents or nodal displacements, remember before said the unknowns of any engineering system are the coordinates of a single vector in Rn. And existence and uniqueness. The rank is the number of pivot points in a matrix. So let's say whether there's a rank in each column, meaning there's a unique solution, or whether there are no solutions, or whether there are infinitely many when there's an existence of a free rank. So in this case, if you look at the right, you see that we have A system matrix, which is impedance in electrical analysis and stiffness in nodal displacements. The known vectors are the current and displacement in the stiffness. The known vectors are the voltages and the load. Okay, this is our first example. Okay, so we're going to take these values and then input them into a matrix. So this is the resistance, as you can see. Cha, 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 you can see. Okay. Now, as you input these values, you see it's Ri equal V. Equal V. No, there are either two ways of solving this. We could row replace. We could row replace. We could row replace until we find a solution. I think that would be the easier way rather than, let's say, inverting the matrix and then using the inverse to get the value of I. So we could do, so if we do this, hold on. Yeah, if we do this, so let's say we have 6 minus 4, 0, minus 4, 13, minus 6, 0, minus 6, 11. It'll take quite a long time, row reducing. So the answer is just, let me show you, is 1, 0, 0, minus 2 over 3, 1, 0, 0, minus 18, 18 over 35, 1. And then we have 5 over 3, 20 over 31. And we have 286 over 137. So we just use backward substitutions and our values should arrive to this. Then check the determinant, just make sure that we have a unique solution, if it's not 0. Next, we're going to go to show you nodal displacement. So nodal displacement, we have Ku equal F. K stands for the stiffness, U stands for the F stands for the force, K stands for the stiffness, U stands for this displacement. So I look for the displacement U. So here I feel like we should take, because we only have like this at 2 by 2. So we can just say U is actually equal to just K inverse times F. When you do this in such a manner, we can just get the inverse of this, which will have to just get the determinant. We get the determinant. Then we put it 1 over d k times this 1140 minus, which will be now plus 42 and minus plus 42 and 2000, and then this AD will switch. So it's gonna be 1000, 2000 up here, then 1000 down here, and then 42 up here, 42 up here. Then pump, we're going to get the inverse, and then we can multiply that by F, and we should get these two values over here. And then when you take these values, we can use the axial force and then compute the actual force in newtons. Okay. As you can see, it's the same algebra, just different physics. System matrix, we have the impedance matrix. In this one, we have the stiffness matrix. Unknown vector is the mesh current, is the displacement U. Driving vector, source voltages, applied loads F. Symmetry, this is your Kirchhoff's law, and this is your Maxwell-Betty's law. Both R and K are symmetric and positive, infinite, because stored energies are correct from. The vector space structure isn't an approximation, it's the exact geometry of energy in linear systems. Once you see their knowns as vectors and the physical law as a map, circuit analysis and structural analysis are the same problem in different units. Thank you for your time.
Hi, my name is Dan Mingjie, and I would like to introduce the application of vector space in science and computing field. Let me introduce the word embedding first. So, here is the idea. A language model doesn't see words the way we do, it sees numbers. Every word gets turned into a vector that acts like a coordinate in space. Take the word cat for an example. For computers, what they see are 300 numbers, like 0.27, negative 0.61, 0.44, and so on. Each number is one learned feature of meaning written in R300. We can't picture 300 dimensions, so on the right I have flattened it down to 2. And notice what happened. Cat, dog, and puppy sit close together. King, queen, and prince form their own cluster. Car and truck sit apart. Words used in similar contexts and are near each other. Closer in space means closer in meaning. When words are vectors, we can measure their relationship by using the angle between them. The two is cosine similarity. The formula is this. On top, the dot product of the two vectors multiply matching coordinates and add them up. On the bottom, the two length width cancel out the sides. So we're left with the pure direction. A small angle gives a value near +1. Same meaning. 90 degrees gives 0, unrelated. -1 means opposite meaning. Look at the numbers. Cat and dog score 0.996, almost the same direction because both of them are animals. Cat and car only score 0.367 because animal and vehicle are not in the same category. And the beautiful part is, even can do arithmetic on meaning. Take king, subtract man, add woman, and you can get the queen. By using a better addition, large language model can make their own sentences. Next, let's go to the spacecraft. To describe where a spacecraft is and how it's moving, we need two things, position and velocity. Position is three number, x, y, z, and velocity is three more, vx, vy, and vz. Stack all three stacks together and you can get one stack vector. It's a single point in 6-dimensional space captures everything about the craft motions at one instant. Combined with Newton's law, we can steer the aircraft. To change the course, the engine fire a burn, adding a velocity change delta v to the current velocity. By using vector addition, we can measure the Earth to Mars transfers. You will get about 9,400 meters per second of total delta v. Here's my favorite trick in all of space flight, the gravity assist. A spacecraft flies past a planet and steers some of the planet's orbital speed, gaining velocity while spending zero fuel. How? By using the pure vector addition. Its speed relative to the planet is one vector, v real, and the planet on orbital velocity around the sun is another, v planet. Add them, you can get its speed in the sun's frame, which is this formula. Look at the triangle on the right. Two arrows join tip to tail produce a much longer resultant row. Here is a real example. In 1979, Voyager 2 flew past Jupiter. It arrived at about 10 kilometers per second and left at about 23, a net gain of 13.4 kilometers per second, all of it for free. The planet's gravity did the work, and the bookkeeping was just adding two vectors. The planet's gravity did the work, and the bookkeeping was just adding two vectors. So, let's tie it all together. One idea carry every example today. Henry defined the vector space, span, basis, and dimension. Sava put it together in circuits and structures, current, voltages, and force. And I send it into AI and orbit. Difference field, the same arrow we draw on the whiteboard wire up circuit. Go up building, still spacecraft, and teach machine to read. Define it, engineer it, launch it. Same vectors, just a much, much bigger stage. Thank you.